Hello, Math 1332 students. We're going to talk about DeMorgan's laws that pertain to symbolic logic. Remember, we had DeMorgan's laws in chapter 2 when we were talking about the complements of intersections of sets and the complements of the unions of sets. Here we are talking about it again. These two are closely related. If you would like to see exactly how they're related, just shoot me an email and I'll be happy to just go into details on that. But this also is I'm going to show you how to prove a tautology. Okay? So DeMorgan's law, look here in the middle here for a minute, one of them is that the negation of a disjunction is the same thing as the conjunction of their negations. Okay? How do you prove that one expression is logically equivalent to the other in all situations? This is how it's done. So let's just look at the left-hand side here, this expression, the negation of P or Q, and make a truth table for it, right? So again, two propositions, so therefore we have the four cases in the standard format. To be able to give you the truth table for the opposite or the negation of P or Q, first I need to talk about what P or Q is. There is that usual disjunction. True in practically every case, only not true when F, P, and Q are both false. So its negation, just flip all these trues become falses, this false becomes a true. Versus, let's see what happens if we look at the expression on the other side. That's not P and not Q. So in these four cases, we need to come up with, we need a not P, I have that over here. We need a not Q, that's over there, and their conjunction. So not P and not Q, false and false is false, false and true, false, true and false, false. This is that conjunction that's false all the time unless both are true. So when not P and not Q are true, then their conjunction is true. Then you make the argument, look, the truth table, the truth values are exactly the same on either side of the expression in every single case. That means we can now write these three bars, which are saying that this expression is logically equivalent to that one. Okay, so DeMorgan's law, a way of thinking about it, so you don't have to write it out every time or think about it, the negation of the disjunction. So this is like talking about the complement of the union, right? You sort of distribute that negation through there. Every proposition gets negated, and the disjunction flips and becomes a conjunction. It feels notationally just like what we did in chapter 2, DeMorgan's laws. Okay? If you should stop the videos right now and prove to yourself the other DeMorgan's law. Okay? You go through that, stop, go work that all out, then come back and see if you have the same thing that I have here. The other DeMorgan's law, that the negation of the conjunction is the same thing as kind of distributing the negation through there, not P, not Q, and that becomes a disjunction here, or not P or not Q. So again, go through all the cases in the standard form. Okay, when you go to enter them in your My Math Lab problems, they should always, first two columns should already be fixed, and you're just entering what goes with those standard cases. P and Q, remember that's only true if both are true, so all these others are false. The negation of that is it's false in the one case and true everywhere else. On the other hand, if you wanted to find not P or not Q, You would need a not P column, you would need a not Q column. Now do the disjunction. False or false is false. That's the only time it's false. False or true, true, true or false, true, true or true, true. So again, you make the argument. These are exactly the same truth values in every case. Therefore, this expression is logically equivalent to this one. We'll use the 3 bars to represent that.